Hi everyone, Mrs. V here, and today this is the third part of our series on Dalton's law of partial pressures. Today we're going to look at calculations involved when you collect a gas over water. So let's get the whiteboard on, talk about what is collecting a gas over water and why we need Dalton's law of partial pressures. Often when you're doing experiments with gases, a really convenient way to collect them is by collecting the gas over water. What that means is you bubble the gas up into a container full of water, and the water will displace, the gas will displace the water in the container, and this way you can actually collect a gas quite easily. So here we have a diagram of collecting a gas over water. Of course, collecting a gas over water is only sensible if your gas has a low solubility in water. Otherwise, your gas is just going to dissolve in the water and you're not going to collect it. So when you are collecting the gas, in the airspace above the water, you have the gas, but you also have some water vapor. If you've got some water, some liquid water here, we've got a closed container, there's an equilibrium set up. Some of that water is always turning into water vapor, and some water vapor is always turning into liquid water. And because of that, what you're collecting is not a pure gas, you're collecting a mixture. So this is going to be a mixture of the gas you're collecting and some water vapor. And we know who to turn to when we need to do calculations involving mixtures of gas, don't we? This is where we have Dalton's law of partial pressure. It says in a mixture of gases, the total pressure is equal to the sum of the individual pressures of each of the gases in the mixture. So in your case, if you're collecting a gas over water, there are only two gases, water vapor and your gas. So your total pressure is going to be equal to the pressure of the gas you're collecting plus the pressure of water vapor. Now, this equilibrium situation where the liquid water is turning into water vapor and some water vapor is turning back into liquid water, the higher the temperature of the water, the more likely it is for this to be occurring, and the less likely it is for that to be occurring. So you're likely to have more water if your water temperature is higher, because you're simply going to get more evaporation and less condensation at a higher temperature. But luckily, you can look up what the pressure of water vapor is at any temperature you like in data tables. So here's a water vapor pressure table. Supposing you're doing an experiment, you're collecting a gas and your lab is sitting at a balmy 21 degrees, then you know that at 21 degrees, you are likely to have a vapor pressure of 18.6 millimeters of mercury of water vapor. So in our equation over here, if the water's at 21 degrees Celsius, then this value is going to be 18.6 millimeters of mercury. So if you have your total pressure in millimeters of mercury, to get the actual pressure of your gas, you're going to need to subtract the pressure of the water vapor. So it's important to know what temperature your water's at, so you know how much of the pressure you're reading is actually the pressure of the water vapor. Let's have a look at an example. I've got one that I'm going to do for you and one that you're going to try for yourself. So a sample of potassium chlorate was heated and decomposed. So we're producing a gas here, oxygen gas. It was collected by displacement of water at 22 degrees Celsius. So we know the temperature. So you could look up, you could go to your table and look it up, but in this case, most times the question will tell you what the vapor pressure of water is at that temperature. So the resulting mixture had a total pressure. Our total pressure here is 754 torr, and our volume is 0.650 litres. So how are we going to solve this problem? We need to calculate the number of moles of oxygen. So that's what we're aiming to do. How do we go about that? Well, for a gas, if we're looking for a number of moles of a gas and we're not at STP or SLC, then that means we're going to be using the ideal gas law. Now, number of moles is what we're after. So we want moles is equal to PV over RT. Do we know? What do we know out of this? We know the volume. We're told 0.650 litres. We know the temperature is 22 degrees Celsius. Of course, we will convert that to Kelvin. And we know R because it's a constant. This is what we need to find out. But the pressure of the oxygen gas is only part of the pressure of 755 torr. So 754 torr is equal to the pressure of the oxygen gas plus the pressure of the water vapor. So we're going to need to, if we want that pressure of oxygen, we're going to need to have our 754 and we're going to need to take the pressure of water. Luckily, we're told that, or we could go look it up in a data table if we weren't told. So we're looking at 754 take away 19.8 torr. Now we've got a strategy for solving our problem. We just need to work through it. So our pressure of oxygen here is 734 torr. And to find the moles, we need to either convert, we can either find the ideal gas constant, the universal gas constant for torr, or millimeters of mercury, or we can convert torr into kilopascals. I think I'm going to convert my 734 torr into kilopascals. Come back here. So 734 torr, using the multiply by 1 method, I want kilopascals. So I've got 101.325 kilopascals over 760 torr, or 760 millimeters of mercury. The torr will cancel out, and I end up with 97.9 kilopascals. Now I'm ready to go. I know I need my temperature. My temperature is 22 degrees Celsius and 22.0 degrees Celsius. And I'm going to have to add 273 to that. And I'm going to get 295 Kelvin. Now I'm ready to go with my moles is equal to pressure. times by volume over R times by temperature. Sub in what I've got. I know I've got 97.9 kilopascals, a volume of 0.650 litres, over R, which is 8.31, multiplied by temperature, which is 295. Run that through the calculator, and my number of moles turns out to be 2.60 times 10 to the minus 2. So really just an ordinary old gas, ideal gas equation problem, but you must separate, you have to use that Dalton's law first to work out what the pressure is of the gas you've collected. Here's one for you to try. This time a sample of hydrogen gas collected over water at 25 degrees. The vapor pressure of water is 24 torr and the volume is 0.5 litres. And there is a total pressure of 0.950 atmosphere. You've got a mixture of pressures here, and what you need to do is find the partial pressure in atmosphere and the number of moles of hydrogen. Okay, I've given you the answers there so that you can check your work. Good luck with that one. I will see you in the next video.